Right, we're going to be studying about quantum physics today, and we're going to be explaining the concepts of the particle behavior of waves so that we can actually open up that whole can of worms of, like, is matter, is matter waves, or is waves matter, is matter and waves something else. Now, legit, that's how it is. Like, very, what is it? I don't.
Gold leaf experiment.
Yes, gold foil, gold leaf, yes. So basically, they did this experiment, right? They took a block of zinc and they put it on top of a negatively charged electroscope. And basically, only when you shine ultraviolet light or any frequency above ultraviolet light, the deflection decreases. So, which was pretty much alright to start off with. Maybe that the ultraviolet light gave electrons energy, and these electrons took this energy and basically escaped the metal. Now, the problem with this is that when this experiment was done, if you assume that UV light is a wave, then you don't need to actually have UV light. You can do it with any wavelength or any frequency, provided that it has enough intensity. You say you just, instead of UV light, if you use violet lights, and you put lots of violet lights around the zinc block, then it should shine. One of the analogies I use is, say there's a water tank, and there's a pipe which enters the water tank, and when the flow is 10 liters per second or higher, the tank fills up almost instantly. But say the flow through this is 9.9 liters per second. We run this for a few moments and then we open the tank and it's absolutely empty. Does that sound acceptable? It doesn't, right? So, say for example, we try that with even more pipes. Say I put another pipe which is 9.9 liters per second, and then another pipe which is doing 9.9 liters per second, and then another pipe which is doing 9.9 liters per second. So now, if you have 4, then obviously it's more than 10 liters per second, right? But still, even if you run this for the entire day and then you open the tank, it's like as if the tank is empty. It's unacceptable, it's ridiculous, it's funny. So this was what this behavior was showing. The fact that UV light was needed to do this, and just a slightly lower violet light frequency wasn't able to do this, even if you increase the intensity, was absurd. That did not agree with the wave theory. Just the same way water does not behave like this, right? So that was an issue. So the first issue we saw with this experiment is this. Number one is that the presence of a threshold frequency.
Is it possible to do this with higher frequency?
Yes, anything above ultraviolet was fine. It's like, 10 liters per second to Rupert J. Kunu would work absolutely fine. But, Nahrin's back and she's like, hard to react. So, presence of a threshold frequency. So, yes, anything above 10 liters per second, for example, would fill up this tank instantly. But this is the problem, right? So this is not how water behaves. Similarly, this is not how waves behave. So that's not what was expected. So this was a problem. Second problem, you might have noticed it by now. I've said it a couple of times. If this tank, even if the tank has a volume of 10 liters, how long would I have to run it to fill it up?
A second.
1 second, right? But that's the messed up part. When we turn the tap on, it fills up instantly. Not even a second, not even a moment in time. So again, this is quantum physics.
Define instantly.
Huh?
Like,
Instantly, instantaneous. There is no delay. Yes, literally there's no delay.
Wow.
So
Magic.
this is obviously hypothetical. Obviously water tanks don't behave like that. But if they did, you would say either tank genus, or you would say there's something wrong with the way in which the tank or the water is behaving, right? So this was another problem with the wave theory, which didn't match up with this, because we're seeing this happen and that shouldn't be happening. The thing that they saw was basically an instantaneous emission. Right? There shouldn't be instantaneous emission. If this is a wave, according to what we were saying, number one, violet light should cause emission of electrons, and number two, even if you had one violet light, the emission would take a little more time, because it would take more time for the energy to reach the electron collect the energy and then get out of it. And if you use ultraviolet, yes, maybe it would happen faster, but eventually it would also need time. So, this is something which again disagrees with the wave theory. Disagrees with the wave theory. And number 3, last but not the least, increasing intensity. Increasing intensity of light does not increase maximum kinetic energy of electrons. So that's basically the third issue we saw. Again, this shouldn't happen. What I'm saying is basically, if you increase the number of violet lights, you're basically increasing the amount of energy which the zinc block is receiving. And if that's the case, then eventually the zinc block should have electrons being emitted from it with greater energy. So these were expected, but these 3 things was telling us otherwise, that waves were not behaving exactly like waves. So a lot of people were confused about this, and a lot of people actually did come up with a couple of nice ideas. And one of the complete and most nicely set of ideas, we had Max Planck, we had Louis de Broglie, we had Einstein, we had Schrödinger. We had a lot of people working in quantum physics. And eventually, what the thing that everyone agreed on, or basically said, was here, light is not behaving like a wave, but instead is behaving like particles. The particles don't look like this, I'm just showing them because it's an easy way to represent it. Where each particle was called a photon. Right? Photons are basically quantas or packets of electromagnetic radiation. So a photon basically is like a light particle. So UV light would be like this. And the energy of a photon, E, is equal to HF. That's basically what we understood. So, do you guys know the equation that Einstein got a Nobel Prize for?
QG equals to MC squared.
Interestingly, that's not what he got a Nobel Prize for. Everyone thinks Einstein got a Nobel Prize for the equation E is equal to mc squared, but he didn't. Do you know why he didn't get it? Because it wasn't proved. So he didn't get a Nobel Prize for this. He actually got a Nobel Prize
For ADA.
for work in this, not for this equation, but for an equation which comes from all of this. And the equation he said was basically, it's so simple that you can just say it in a very commonsensical manner. And imagine that's what Einstein got his Nobel Prize for. The thing he said, or the rule he said that brought him the Nobel Prize was basically, what would you do with the energy of the photon? You would use it to first get the electron out of the metal, and the remaining energy would be used to give the electron kinetic energy to get out, right? So he wrote that in words, or basically as an equation. He wrote energy of the photon, HF, is used to number 1, this is phi, right? Basically phi is the minimum energy required to get the electron out of the metal, plus tomar ja energy baki thakbe, whatever energy you'll have remaining after that, plus half mv squared.
Kinetic energy.
Yeah. So
H
yeah.
is Planck's constant, right?
Yes, h is Planck's constant, f is frequency, work function, plus half mv squared. You can say max, because there's going to be a range of kinetic energies. The ones which come out deep from the metal will have less kinetic energies. The ones which come off the surface of the metal will have more kinetic energy. So basically, this is the equation that he got his Nobel Prize for. And then he gave all the money to his wife. Do you know
Which
that?
one?
The first one. And told her to go away. Legit.
Oh, what a rock star.
That's good.
Bechari Tapure went and bought 3 houses with that money.
How should Bechari?
Huh?
Think about it, so how should Bechari?
No, eventually I think ওটা ইয়ে করতে পারে নাই মানে. Well, obviously you don't remember about Einstein's wife's 3 houses, do you? You remember about Einstein's equation.
Not sure about it.
So yes. All right. So basically this is what we saw happen. Right? I'm not talking about Einstein's wife, I'm talking about waves. So basically this proves a very fundamental and very important thing. What this proves is that light sometimes behaves like particles. Why? Because of these. Now, I'll just go slowly through all of these again and explain what you should expect if light was a wave and how we explain this. So if light was a wave, you shouldn't have a minimum ultraviolet frequency to cause emission. Any frequency, provided you give enough energy, should cause emission. There shouldn't even be a threshold frequency if light behaved like a wave. But because it's behaving like a particle, we see that it's actually requiring a minimum frequency. And that makes perfect sense. The electron will only get out if the photon it has to interact with has enough energy. If it doesn't have enough energy, it won't even interact with that photon, right? One of the analogies I use, again, it might sound a little inappropriate or a little sexist, is say, for example, a girl wants to get married. So so everyone's like, okay, so we got her to meet 500 guys and she doesn't like any of them. Like, what sort of joke is that? Well, one thing you have to realize is, তুমি যদি 500টা guy, if all 500 of them are rickshawas, and if she's not into rickshawas, then most likely she wouldn't be okay with that, right? So, then again, that doesn't mean that she's of high standards or anything, blah, blah, blah. She's just looking for someone who she finds comfortable to marry. And she has the freedom to choose whatever person she wants because she has to pick only one person, right? So I know this is not the best analogy ever, but it's
there.
So she looks for a photon with the right frequency.
Enough energy, right? She looks for a photon which has enough energy, or basically enough of what her requirements are. So it's like the people that she would meet but not marry, these would be like, even if you had high intensity violet light, none of the photons have enough energy to actually
So that's like
excite
even
it.
if it wasn't a rickshaw, if it was
It was a rickshaw.
taxi wala,
So even if
Many different ranges,
Yeah.
right?
So even if you gave like a bunch of high frequency violet photons, it wouldn't work.
It wouldn't work, basically, because these photons, the violet photons, wouldn't have enough energy to even excite one electron out of the metal. It doesn't exceed what we call the work function, right? So if it doesn't have enough energy to get the electron out, even if you send multiple photons, it doesn't matter, because electrons can only absorb energy from a photon. So what happens? You shine so much light, but nothing comes out of it, and that's because the electron can only interact with one photon. If this was wave theory, then we wouldn't have any of this minimum one particle interaction, right? It would just sit there, it would collect energy from all of the energy that's falling on it, and then eventually get out of it. So that's not what happens. So that's why basically we end up saying this, that the presence of a threshold frequency proves two things. Number one, that light is behaving like a particle, and number two, the electrons absorb energy from only one photon, and that one photon it will absorb from is obviously a photon that has enough energy to get it out of the metal. Number two, instantaneous emission. Again, this disagrees with the wave theory, because if it's a continuous supply of energy, even if it's a high frequency wave, this wave will take some time to interact with the electron and then get out, right? But because it's coming as one entire packet, it comes in one go and goes out in one go. It's like that, right? That's why it's instantaneous. That's why it's possible, because it's one packet. It receives the energy in literally a packet. That packet has no dimensions. No, it's not like it has size and shape and this and that. So basically it gets it in one go and it emits it instantaneously. So that's what instantaneous emission shows. Again, that the wave is reaching it in the form of packets and not in the form of waves. And increasing intensity does not increase the maximum kinetic energy of electrons. This brings us back to pretty much the first thing that we said. If you had a lot of violet lights, right, and if the electrons was taking energy from the waves, then the more violet lights you would have, the electrons would take more energy, which would mean they would have more kinetic energy. But we see that that does not happen. What does happen is that the electrons are actually emitted with the same amount of kinetic energy, right? If the frequency is the same, the kinetic energy remains unchanged. And this is nicely explained by this. Again, basically, the kinetic energy of the electron depends on the frequency of the photon, not on the number of photons. And that is why we have this behavior. Does this make sense? Right? You guys look a little confused about all of that.
Too much.
Yes, a little too much for today,
So
but
this
yes.
means that light has both momentum and a wavelength.
Yes, yes. Why do we know that light behaves like a wave? Because it diffracts. It goes through double slit diffraction. With anything that goes through double slit diffraction, or diffracts basically, or interferes, must be a wave. So that means light is a wave, because it goes through double slit interference and then interferes and everything. And light must be a particle because of photoelectric effect. So what is light? It's like a
Magic.
particle, but not exactly a particle. And it's like a wave, but not exactly a wave. It's this thing in between. And we'll keep it for another day. But these things in between, which can be particles and waves, are aware of when you're watching it.
What?
Yes.
Oh, this is
Oh,
something
wow.
to do with like superposition, Kijani. Like you look at it and then Kijani ekta.
But how?
It's like, scientists.
Frequency of the photon is basically frequency of the wave which creates the photon. So yes, that's what it is. That's what it is, guys. All right, then, guys, we're done for tonight. We're done with the basic introduction of quantum physics. We'll be going into more depth later on. All right, then, guys, see you soon. We'll be back in a few days, a little gap, and then we'll continue from where we're leaving off. If you have any questions or any queries, please send them to us on the page, and we'll be able to help you out answering them. Don't worry, guys, your exams are close. I know it's time to panic, but we're here to let you panic a little less. Good night, guys. Take care. And until next time on Rafale Teachers. Oh, yes.